2021 projectile motion, let's do it. The picture on the right shows a bike rider going over a ramp. The rider's speed at the top of the ramp is 10 meters per second. The angle between the ramp and the ground is 30 degrees. The top of the ramp is 1.1 meters above the ground. B. The vertical velocity of the rider just as they leave the top of the ramp is 5 meters per second. Calculate the maximum height that the rider will reach above the ground. Okay, so what we have to do here is we have to see what we have and what we don't have. And so I always start off by drawing myself a table, okay? And so I've got the horizontal components here and the vertical components here, and I do not mix them up. So because we want to find the maximum height, this essentially is the distance that this rider will reach vertically. The highest maximum height, aka the distance. So this is what we're trying to figure out. What else do we have in terms of the vertical plane? We know that the rider, as they leave the top of the ramp, their initial vertical velocity is going to be, VI, is going to be 5 meters per second. What else do we know? We know that acceleration due to gravity is 9.8 meters per second. And vertical velocity right at the tippy top, we can make that our final velocity because we're only measuring how high it goes to the top point here. So the velocity at the top, VF, is going to be 0. And I guess that's all we kind of need to work out our maximum height, our distance. What is a kinematics equation that we can use to figure out distance, how high it goes? Have a look at your resource sheet, pick the kinematics equation which uses all of these variables. What I'm going to use is VF squared equals VI squared plus 2AD, substituting everything in. However, before I get to that part of substituting everything in, I have to define my positive and negative, what do you call them? Yeah, vectors. Got there in the end. So, if we look here, we know initially, to get to the top point, this rider's velocity, initial velocity, is upwards. So VI is going up. I always suggest that your velocity, the direction of your velocity, keep it a positive. Always make it a positive, okay? So in this instance, the rider's going up. Let's make that a positive value. Acceleration is going down, okay? It always pulls the rider down, okay? This is because of gravity. And because it's opposing this upwards velocity, we make the acceleration a negative value. So in our calculations, we have to make 9.8 a negative value, and we leave the initial velocity as a positive. VF we don't have to worry about because it is at 0 meters per second. Okay, so now we could substitute everything in. So VF is 0. VI is 5 squared plus 2 times negative 9.8 times distance. That's what we're trying to figure out, okay? And so we need to rearrange this whole thing to get distance. Again, you may have seen my previous tutorial that this right here is the center of the onion, and everything around it are the layers of the onion that you have to peel one by one. And so to peel an onion, you have to peel the outside layers first, and then you peel the inside layers. So I'm just going to show and visualize that for you. So the first thing we're going to get rid of is the 5 squared, okay, because it's the outside layer, and you peel the onion from the outside in. So to get rid of plus 5 squared, what do? You have to minus 5 squared from both sides of the equal sign. So 0 squared minus 5 squared is going to be 5 squared. And what this leaves us with is 2 times negative 9.8 times distance. Whenever I see something being multiplied with something else, I can smush them together to simplify the equation. So what this turns into is 2 times negative 9.8 is negative 19.6 times d. Okay, so I'm almost there. I need d all by itself. So what I'm going to do is I need to get rid of this negative 19.6 because it's being multiplied. The way to get rid of it is to divide it by itself on this side. And that means I have to divide the other side by the same thing. And so I'm left with d equals negative 5 squared over negative 19.6. And so, plugging that into my calculator, I am going to get 1.28, okay? So we've worked out 1.28 meters, let's not forget the units. I have worked out that this is the distance, peak distance from the top of the ramp. But the question is asking us what's the maximum height above the ground, okay? And so we can see in the diagram that from the ground up to the top of the ramp, it's 1.1 meters. And what I've worked out is from the ramp up to the highest point is 1.28. So to work out the maximum height, I have to plus 1.1 with the 1.28 that I've just worked out. So in total, d total vertically is going to be 1.28 plus 1.1, and that is going to give me 2.38 meters. Let's move on to C. The diagram below shows the path of the rider when they leave the top of the ramp at 30 degrees at 10 meters per second. So this is the resultant velocity, the combined velocity, which incorporates the horizontal and vertical components. On the same diagram, and without further calculation, sketch the path of the rider who leaves the top of the ramp at 40 degrees at 10 meters per second. So at the moment, this is at 30, okay, and we want to show what the projectile will look like at 40 degrees, okay? So at 40 degrees, it's actually going to end up further, okay? Oh, that's not what I wanted. It's going to end up, let me draw in red, it's going to end up further. And you may have thought that it's going to end up shallower or like closer, but the thing is, because it is less than 45 degrees, it's actually going to go further than it is going to go higher. If it were to be over 45 degrees, it would be more of a steep projectile. But because it's less than 45 degrees, it is going to go further than it is going to go higher, okay? For a rider leaving the top of the ramp at 30 degrees at 10 meters per second, calculate the vertical speed of the rider when they land on the ground. AKA, we want to find out the final velocity, and we want the vertical final velocity. Okay? How are we going to do that? We need to figure out what values we have and what values we don't have. This is how I always start out, okay? So we're not really concerned with our horizontal components. We are concerned with our vertical components, and the thing we want to find is VF. Okay, so we're going to write that down. we know that VI is 5 meters per second. It's not going to be 10 meters per second because this is the resultant. Okay? It's the result or the combination of the vertical and the horizontal. So we don't use that as our VI. We have to use the 5 meters per second because that's the vertical initial velocity. Okay? So VI is 5 meters per second. Acceleration is 9.8 meters per second. And what else? We don't know anything else, okay? So what do we have to do? We need to pick the correct kinematics equation, which is going to allow us to work out what VF is, okay? Before we move on, we actually do know something else. We know that the distance from the ramp to the ground is going to be 1.1, okay? 1.1 meters. So this is going to be how far this rider is going to fall, okay? And so now we can pick our kinematics equation. I'm going to pick VF squared equals VI squared plus 2AD. That's the one that I'm going to pick because it involves all of the variables on my table on the vertical side. And before I move on, remember we have to define what our positive and negative vectors are. So VF is what we're concerned with, okay? VF is going down, okay? VF is going down, so I am going to make that a positive value. VI, on the other hand, okay, VI was initially going up, okay? VI is initially going up, so it is going to be negative in relation to my VF because it's going in the opposite direction, okay? Then I've got gravity, which acts straight down on the rider, okay? Straight down on the rider. And so because it is going in the same direction as VF, which is my anchor point, I'm going to consider that my anchor vector because I'm comparing every other vector to it. It's going in the same direction as VF, so I'm also going to make gravity a positive value, okay? I'm not sure if this makes too much sense to you, but I'll try explain it in another way. Skip ahead if you don't need the extra explanation, but I'm going to show you what I mean based on this diagram. So VI, okay, initially this rider is going upwards to this peak point. So VI, the vertical initial velocity, is going up, okay? The final velocity as the rider goes down, okay, is going in this direction, okay? So the velocity of the rider as they go down on the journey is pointing downwards. Gravity is, throughout the whole flight, is also acting downwards. I have decided to make VF, this is VF, I don't want a highlighter, I've decided to make VF my anchor vector, okay? It's because it's the thing that I'm trying to find, and I'm comparing all the other vectors around this vector, okay, in relation to this vector. So VF, I'm going to define it as a positive because it's my anchor vector, it's my vector of concern, the thing I'm trying to find. So in comparison to that, I have VI over here, the initial vertical velocity, and it's going in the opposite direction to VF, so I'm going to make that a negative vector, okay? And then finally my acceleration due to gravity is downwards. It's in the same direction as VF. It's not opposing it. So I get to make this a positive value, okay? So hopefully that makes a lot more sense. Just got to pick one vector of concern as your anchor vector, and then assign negatives and positives to the other vectors around it. Okay, so back to the calculation. Now we can substitute everything in. Now that we've defined that VF is going to have to be a positive, VI is going to be a negative, and acceleration's a positive. Okay, let's substitute. VF at the moment is unknown. VI squared is 5 squared. Okay, and we know that's a negative at the moment, plus 2 times 9.8 times 1.1. Okay, so what I want you to understand is that if we have a negative 5 squared, it's going to end up being a positive. If you enter it into a calculator correctly like that, it'll be a positive 25 plus 2 times 9.8 times 1.1. Okay, and so what this equals, doing BEDMAS, you will get VF squared equals 25 plus 21.56. Finally, we're almost getting there. We'll get, plussing these two values together, 46.56. And now to get rid of the square, we have to take the square root of both sides. And so we'll be left with VF equals 6.82 meters per second. So that's our final velocity, okay? So going back to the question to remind ourselves, calculate the vertical speed of the rider when they land on the ground. So right at this point over here, VF equals 6.82 meters per second. Okay, cool. So now that we've done that, we can move on to the last part of this whole problem. Here's what we need to do. Calculate the horizontal distance traveled from the ramp where the rider lands on the ground. Okay, so how far does this rider end up? Okay, we want to find this horizontal distance. So again, you know I love tables. So what we have is our horizontal components and our vertical components. We know that for our horizontal stuff, the equation that we use is V equals D over T. And so what we want to find is the horizontal distance. Okay, so how do we do this? Well, we need to first find the vertical velocity component, and we need to find time. Okay, so what do? Let's first work out the horizontal velocity. How do we do that? Well, we know that the resultant velocity is 10 meters per second. We know that the vertical velocity is 5 meters per second. And we want to figure out this horizontal component. How's it, what's its velocity horizontally? Let's label our triangle. We have our hypotenuse over here. We've got our opposite over here because it's opposite this angle of 30 degrees. And we've got our adjacent over here. So we have our hypotenuse, an angle, and adjacent. So I'm going to use K because we're using our adjacent and hypotenuse, and the equation I'm going to use for this is cosine theta. Cosine theta equals A over H over H, substituting everything in. Adjacent is what we're trying to figure out. H is 10. To get rid of the 10 on this side, I have to multiply it by itself. That means I have to times this side by 10. And then I've got A equals cosine 30 times 10, which is going to be 8.660 meters per second. So we know that the horizontal velocity, okay, is going to be 8.660. Now what we can do is we can work out the time, the total time it takes for this rider to land, okay? So let me just show that working out. If we think about it, time, remember, is the linking factor between the vertical and the horizontal. So however much time it takes for the rider to go up then down is the same time taken for the rider to go completely across. So how do we work time out, the total time? As we can see here, the rider is starting off at this point, okay? So if we work out the time taken, let me just make this diagram a little bit clear. I'll use a highlighter. If we first work out the time taken for the rider to get to the topmost point, then we can work out the time taken to get from the topmost point to the bottom point, okay? And if we plus those two values together, we'll get the total time. We cannot calculate the time taken to get halfway to the peak and times by 2 because it's not an even projectile, okay? It's starting off at an elevated surface. Right, so our first mission is going to figure out the time taken to get to the top. Time to the top. Okay, what do we do? Well, in our vertical component, okay, in our vertical component of our table, we know that acceleration is 9.8. We know that the final velocity at the top is going to be 0. We know that VI is 5 meters per second. And what else do we know? We know that the maximum distance from the ramp to the top is going to be 1.28, because we're trying to figure out the time from the ramp to the top, not from the ground to the top. So distance is 1.28. The thing that we want to figure out is time to the top. What is that going to be? So using all these values, what's a kinematics equation that I can use? I'm thinking that we use VF equals VI plus AT. Okay? Feel free to try a different one. I'm going to use this one. And so let's go ahead and work this out. Right, VF, something that we have to do is define our positives and negatives. So if we think about it, initially, the rider is moving upwards, okay? So the initial velocity is going to be positive. That's our anchor vector. VF is 0, so we don't have to worry about that. Acceleration, on the other hand, is going down. So because VI is our anchor vector, our reference vector, acceleration is going in the opposite direction to our reference vector, so it's going to be a negative value. Okay? Thank goodness I remembered, otherwise we would have stuffed up. Okay, so now we can sort of plug everything in. VF is 0, VI is 5 plus negative 9.8. 8 times t. Okay, so t is what we're trying to figure out. So we want t by itself. What I'm going to do is I'm going to get rid of the 5 by minusing 5 on both sides. So I get negative 5, 0 minus negative 5 is negative 5. So negative 5 equals negative 9.8 times t. To work out t, I have to get rid of times negative 9.8 by dividing it by itself. That means I have to divide the other side by itself. T equals 0.510 seconds to the top. Okay, so we know the time taken to get to the top is this right over here. So now what we can move on to is time taken from top to bottom. Okay, I've got my horizontal and vertical values. I'm only concerned with the vertical. We want to find the time taken from top to bottom. We know that our initial velocity this time is 0 because we're starting from here. This is our starting point, okay? And so we want to, this is our initial velocity now, and our final velocity is down here, okay? So we're changing our pinpoints. So VI is 0, VF, we've calculated this previously. Oh yes, that's right, it's over here. 6.82 is 6.82. We've got acceleration at 9.8. What else do we need? I'm pretty sure that's all we need. And so, distance. Distance from the top to the bottom. Distance from the top to the bottom is what? We've calculated it to be 2.38. So what's the best equation to use? What I'll use is d equals VIT plus half AT squared. So don't mind me, I'm going to squish everything in here. D is 2.38, VI is 0 times t plus half times 9.8 times t squared. What have I missed to do? I've missed to define my positive and negative vectors. So let me do that now before I continue on. So I'm going to make my velocity, because VI is 0, I cannot use that as my reference vector. So VF is going in the downwards direction. Okay, the final velocity is moving towards the ground. So I'm going to define that as my positive vector. Acceleration is also going down. So in reference to my VF, because it's going in the same direction, it's also going to be a positive. Okay, so I don't really need to change anything to my equation, but it's just good to check anyway. So now what I have to do is simplify it. So I know that 0 times t is just going to be 0. So I can kind of take that out of the equation. Half times 9.8, I can simplify that, smush them together. And what I'll get is 2.38 equals 4.9 times t. I'm running out of room here. So to get rid of the 4.9, I divide this side by 4.9. That means I have to divide this side by 4.9. T squared equals 0.4857. To get rid of the square, I have to square root both sides. And so I'm left with t equals 0.69. Okay. And so this right here is the time taken to get from the top to the bottom. So I've worked out the time taken to get from the ramp, the top of the ramp, to this point here is 0.510. The time taken for the rider to go from the top to the bottom, we've worked out to be 0.696. 0.6969. Okay, and so the total time, T total, equals 0.510 plus 0.6969, and that in total is 1.206 seconds. That is the total time. So finally, we can actually answer the question, which is asking us the horizontal distance. And so we can see over here that we know our total time now, based on this answer here, is is 1.206 seconds. Right, we can finally do all the maths. We've got 8.660 as our horizontal velocity equals distance over 1.206 seconds. We want distance by itself, so we have to get rid of this guy by timesing it by itself. That means I have to times this side by the same thing. And distance, therefore, equals 10.39 meters. And that is our answer. This is how far this rider goes. Okay, so that's how far the rider goes. It goes 10.39 meters. Whew, that was a lot of work. Be proud of yourself, and then I'll see you for the hockey match. Boom.